Okay, so let's look at public key encryption. So we're going to look at the areas that public key encryption is applied into, some of the methods that we use, and also in its application into digital signing. Okay, so what is public key encryption? Well, it's a special method that we can use that allows us to create a public key and a private key, and these are special keys. So what we basically have is a public key and a private key. Okay, so Alice has a public key and a private key. Typically we might draw the public key as a padlock. And with this, Alice can distribute her padlock to anyone who wants to encrypt data for her. And then what we have is a private key, and we'll just draw that like a key here, and it is this private key which can open up the padlock. So the keys work together, so when we use one we can use the other, if we use this one we can use the other one. So with this we can create what's called a key pair, and the two key pairs work together to encrypt and then to decrypt. Okay, so I've got Alice's public key here, and here is our private key. We often store these on a digital certificate, and which is signed by a trusted entity. But let's not go into the usage of digital certificates, just that Bob and Alice have each got a public and a private key. Private key is our key, and then the public key is our padlock. Encrypt with one and decrypt with the other one. And it doesn't matter which way round that we do it, we can encrypt and decrypt with each one. Okay, so what's the applications of public key encryption? Where is it used? Well, there's three main areas that we apply it into, and let's take Bob and Alice. So here we have Bob, and here we have Alice. So they both have their keys, and we'll draw our private key here, and then we have our public key, our little padlock here. Okay, so now in the purest way, Alice wants to send Bob some encrypted data. So this is encryption, just in the same way that we use symmetric encryption. We'll use public key to be able to encrypt something for Bob. So we'll take our data, and then we'll encrypt it, and we encrypt it with Bob's public key. Okay, so Alice gets Bob's public key in some way, usually through a digital certificate. Not this one, but probably this one here, in a trusted way. And then to decrypt that, then Bob uses his private key to reveal the data back again. Okay, so this is standard public key encryption, and we use Bob's public key to encrypt and his private key, which should never be revealed, to decrypt. But there's also other applications for this. So here we have Bob and Alice again. And in many applications, what we want to be able to do is to end up with the same shared key on either side. So how does Bob or Alice get the key over to Bob that is to be used? And we typically do that within a tunnel. So one way of doing this is to pass with public key encryption. So Alice takes the key that she wants. Yeah, it's a randomly generated key probably. And then what she'll do is that she'll actually she'll use Bob's public key. Here's his public key to be able to encrypt the secret key. So we now have an encrypted version of the secret key. She'll send that over, and then Bob will use his private key to be able to decrypt the key, and he'll have the same key as Alice. So this is key exchange, or a key exchange mechanism. It's not perfect, and in TLS 1.3 this method has been dropped because a long-term hack of, or a hack of Bob's private key could reveal all of the keys that Bob and Alice have used in the past. Okay, but it's certainly possible to use this mechanism to be able to pass a shared key. And then the last method that we have, that we use public key encryption for, is to identify Bob to Alice, and to also provide integrity into messages. And we call this digital signatures. A typical method is called ECDSA. And with this, we have our keys. Okay, there's the private key, and here is the public key. Public key and private key. And what we do is that we take a message, and in this case we'll say that Bob has the message, and then we take a hash of the message, and from there we then encrypt this hash to create a signature. So I'll explain in another talk what the signature actually looks like, but it's really Bob's private key and the hash of the message added, and then we send that along with the message to Alice. Yeah, so we send the signature along, and then Alice will take her own hash. She then uses Bob's public key to check the signature of it, and if the two signatures tie up, then she has proven that Bob was the one who sent it, and also that the message hasn't changed. So this is digital signatures, and it's the third area that we would use our public key encryption. Okay, encryption, public key encryption, key exchange, and in digital signatures. Okay, so let's look at the basic methods that we have for our public key encryption. encryption and how we actually implement it. So what are the methods that are actually involved? Well, the main methods we have is RSA, elliptic curve cryptography, and discrete logs. This method is, the strength of this method is related to integer factorization, or the difficulty in it. This method relates to elliptic curves, and I'll explain that in a little minute. And this method is the difficulty of determining the exponent for discrete logarithms. So that's a log generator base and an exponent. And then in public key encryption, we also have the mod of p, a prime number. Each of them use prime numbers, and I'll explain that in a little minute. So those are the three main methods that we would use to be able to implement our public key encryption method. The method that's most often used these days is this method, elliptic curves. Very, very efficient method, small keys, fast, scalable. These two methods have struggled to be able to keep up with elliptic curve cryptography. Unfortunately, all three methods will be able to be cracked by quantum computers. So we need to move away from these methods in the future. Okay, so let's look at each one in turn. Just move Alice there. Okay, so the first method that we'll look at is with RSA. So with RSA, what we have is that we generate two prime numbers, P and Q. And these are fairly large prime numbers, probably 1024 bits long or 2048. And we create what's called a modulus, and that's P times Q. So if we have a 1024 bit primes, then we have a 2048 bit modulus. So when we talk about 2048 bit RSA, we're talking about two 1024 bit prime numbers multiplied together. The difficulty in RSA is to be able to find the two prime numbers which made up the modulus. And we're probably around the 728 bit factorization of n. So we need to keep well away from that. So that's why we select more than 1024 bits normally to be secure. And a typical value is 2048 or 4048 bit RSA. So we have a modulus value, the value of n, and that's the value that keeps the security of it. And then what we do is that we define a public exponent value. I'll explain what that really means for the encryption. And basically the exponent value should not share a factor with the modulus. So we pick a value of E that isn't a factor of the value that we create. And the value we create is called phi. And phi is P minus 1 times Q minus 1. We then select E, our public exponent, so that it does not share a value with this phi. After this, we create a private exponent or a private key part, and that's equal to the inverse of E mod n. I'll give a practical example of this in a little minute. So this is our public part and this is the private part. In real life, this value is normally fixed at 65537. And then when we calculate our D, it's the inverse of E mod n. And in Python, it's a single line for the inverse mod function to calculate D. D is our private exponent. So let's take a practical example of this and show actually how it works. Okay, so let's take a value of P equal to 3 and Q equal to 11. Both are prime numbers, so that's fine. We then can calculate n. It's easy, 33. Now we calculate phi, and that's 2 times 10, which is 20. We now need to select E so that it doesn't share a factor with phi. So the factors of 20 are 2, 4, 5, and so on. So if we select a value of E equals 3, then it doesn't share a factor with phi. Now what we do is we work out the inverse of E, and if we want to do it long-handed, then we can compute such as this. Sorry, that should be phi there. Okay, so we work out the value of D times E, and that's equal to 1 mod 20. So we could go through the values 1, 2, 3, 4, 5, 6, 7. When we get to 7, 3 times 7 is 21. And when we take mod of 20, that is 1. So the value of D that we get is 7. Luckily, we don't have to do this type of calculation here because in, say, Python, we have a single line of code that will calculate D. But this is how it works out. 7 times 3 is 21, mod 20 gives us 1. So we have a decryption value of 7. So our public key in this case is 3,33, and our private key is 7,33. So the way that we now work this out is that the cipher is equal to the message to the power of E mod n. So in this case we take a message of 5 and our cipher becomes 5 to the power of 3 mod 33, and I think that should give us 26. To return back the value, we take the cipher to the power of D mod 33 and 26 to the power of 7 mod 33, and hopefully that should give us back 5. Okay, so it's this exponent method that allows us to cipher a message. The message is converted into an integer. We raise it to the power of E, take mod n to get the cipher. The cipher is raised to the power of D, mod n, and then we get the value back. Okay, and this is the RSA method, and it works wonderfully. The only problem with it is that it has struggled to keep up with some of the other methods, especially when it comes to the elliptic curve method. So let's look at elliptic curves and see how they work or how they differ from our RSA method. Okay, so we'll just take elliptic curve and we'll look at elliptic curve cryptography. And with elliptic curve cryptography, we have the form of y squared is equal to x cubed plus ax plus b mod p. And where a is a constant and b is a constant too. And this will define our curve. So if we were to plot that, we'd get something that looked a bit like this. It's an elliptic curve shape. The other thing that we have with elliptic curves is we have what's called a base point. And this is going to be the starting point on the curve. And then what we do with elliptic curves is add points together to give us another point. And with elliptic curve cryptography, what we actually do is that we work out a private key value. Let's call it SK. And SK is a random value that we select for our private key. We then create our public key by adding this point SK times. It's equivalent to representing and multiply. But let's say we add G SK times, and we now get our public key, which is this one. So the curve itself is represented by A and B and P, prime number, and G. There's also another one called the order that I won't quite talk about, but the main parameters that we have in defining any elliptic curve is a value of A, B, P, G, and the order O. And G is the base point. A and B are two values. And for a very popular curve that's used in Bitcoin and Ethereum, we have this curve, and actually A is 0 and B is 7. So with Bitcoin, actually it's y squared is equal to x cubed plus 7 mod, and then we have a 256-bit prime number involved with Bitcoin. But with, say, Bitcoin, we create a wallet which has our private key, and that's that value, and then we can easily generate our public key just by multiplying our private key with the base point to get a new point on the curve. So often our private key is 256 bits, but our public key is 512 bits because we're using a point on the elliptic curve. Other curves that you might come across, curve 25519 is a very popular curve, and it's an interesting little curve because its prime number is 2 to the power of 255 minus 19 for curve 25519. If you're interested, the basics of this is that the only two operations that we have is a point add one point to another, and a point double. So we double G to get another point, to G, and so on. The curve doesn't, the points don't look like this when we bring this in, but I'm just illustrating it, what it would look like just like that. When we add the mod P, we end up with lots of dots. But the one thing about an elliptic curve is that if you add one point to the other, you will always get another point on the elliptic curve. It shouldn't be possible for you to get the point which is off the curve. And in this way, we can actually implement our public key encryption. So this is a very popular technique. and it's especially popular with digital signatures, such as an ECDSA, as used in Bitcoin and Ethereum. And there's also another one called EDDSA, which is used in IOTA and other applications. It's a very efficient method, this one, and this one is probably preferred these days over the ECDSA, as it gives us some special properties. Okay, so that's the operation of elliptic curve in there, with a digital signature with something like Bitcoin. So what we can do is that we can have our private key, and if Bob wants to send Alice some Bitcoins, this is Bob, then we take the transaction and then we create a signature which is signed by Bob's secret key. Alice automatically can check, or anyone can check the signature to see that it was Bob that actually signed the transaction. And this was what Satoshi Nakamoto implemented, and he selected this curve here, and basically we can have our secret key, and then we can generate our public key based on this method that we have here. Bitcoin is a bit different in the way that it creates the public key because of the ECDSA, but in the purest form, our public key becomes the secret key times the hash of the secret key times the base point. Okay, so the main parameters that we have with our curve, as I've said before, is the A value, the B value, the prime number, the base point, and also the order. The order is the maximum number of points that we can have on our elliptic curve, and some operations are conducted using that value. As I said, with a Bitcoin, then the actual curve is defined with this. And this is the Bitcoin curve, and this is a 256-bit prime number here. Okay, this curve is used in Key Exchange, and you'll find it with inside ECDH, or Elliptic Curve Diffie-Hellman, and other Key Exchange methods. Typical ones that we also have, ECDH. Along with this, we can have X 25519, which is Key Exchange using curve 25519. Okay, so we can use elliptic curve in terms of Key Exchange in a different way to this one, but we can exchange parameters and end up with a shared key using this elliptic curve Diffie-Hellman method. For signatures, we have, of course, ECDSA and EDDSA. It can also be known as ED 25519 if we use curve 25519. The other method that we use is LGAMO, and that uses discrete logs. The LGAMO method is a purer form of discrete logs, we take a generator value, and we have a secret key of X. So X becomes our private key, and Y becomes our public key. So I won't explain too much more. If you're interested, if you go to asecuritysite.com/elgamo, you will be able to get some practical examples of the Elgamo method. The technique itself is coming back again in popularity because it has some nice properties that we can use for something like homomorphic encryption. Okay, so RSA, elliptic curve, and Elgamo are methods that we have. So finally, what I'd like to do is I'd like to lay out a basic scenario to show how public key encryption and also symmetric key encryption are used together to be able to create integrity of our messages. Okay, so I've got my keys here. Hopefully I can keep a track of them. So I've got Bob's public and private key and Alice's public and private key. Got some certificates over here. That's fine. So what we'll do is we'll start off with Bob here, and then we'll have Alice over here. And what we need to do is to get a message from Bob to Alice, which has been signed by Bob and also is secure. Along with this, we want to be able to make sure there's some integrity so that Alice can tell that the message hasn't been changed along the way. Okay, so let's see how we can do this. What we'll do is we'll generate a key pair for both of them. So this is Bob's private key, and we'll have Bob's public key. Okay, and then over here we'll have Alice's public key and her private key. Okay, they can keep these in a wallet and they can reveal them as required. The private key should never be shown, but the public key can and will be shown. So initially we'll take our message and we'll just make it the word hello. After this, Bob will take a hash of the message, and then we'll add his private key to create a signature. So we'll call it signature B. So the hash is then, we could say, encrypted. It's not quite, but it is signed with Bob's private key. Okay, so we'll see how that's used a little bit later. So now what we do is that we create a new symmetric key. So the symmetric key, and this one here, so we'll just draw it like this. The symmetric key is an AES key, so that's a new key that we're actually going to use to encrypt the message. So we take the message and the hash together, and we'll encrypt them with this new key that we've just created. Okay, and we'll add in the hash of the message and we'll encrypt that whole lot. Okay, so you shouldn't be able to see anything now. So we now have this key, and we'll call that key K. The symmetric key has just encrypted all of this hash and message. So now what we need to do is that we now need to take this key and we need to protect it in some way. So we take the key and then we'll encrypt it with Alice's public key. Okay, so Bob gets Alice's public key and then encrypts that secret key, the key value, with that. And then we can just take this together. That's still got the message in there and the hash the message. Okay, and this becomes message that we're going to send. So let's say this is an email that Bob sends to Alice. Okay, so with this we take Alice's public key and then we encrypt this symmetric key with this key. And what we've done is we've used Bob's private key to be able to sign there. Okay, so the way that we would normally do this is that we would take Alice's certificate with her public key. Okay, Bob would receive this and would check the signing and then take Alice's public key to be able to encrypt that key there. So now what we'll do is we'll send that over to Alice. Okay, so we've got our encrypted hello message, the hash, and there's our hash. And then what we'll do is that we'll decrypt this key with, guess what? We'll decrypt it with the reverse of the public key, which is the private key. So we take Alice's private key, and from there we can decrypt the key here, and guess what? We'll reveal the key that was used to encrypt the message. So once we've got K, then we apply it there and we'll be able to reveal the message, hello, and the hash of the message will also come out because we've decrypted that. Sorry, this should be the signature. Forgive me there. So this is the signature in here. Okay, signature. And this is the signature. Okay, so we take the signature and we add it into there, and this is the signature in there along with the message for that. Okay, so now what Alice will do is to be able to take the message and then create her own hash of that message. And we obviously have the signature here. Alice will then take Bob's opposite of the private key for the signature, Bob's public key. So we'll take Bob's public key here with the hash, and then hopefully we'll produce the same hash as that. Alice will check those two values, and if they're the same, she knows that it was Bob who signed the message, because only Bob would have the private key that's associated with his public key. So we need to find some way to get Bob's public key over, but I'll explain that in another talk. So what we've managed to do is that we've proven that Bob signed. We've proven the integrity of the message, that it hasn't changed, and we've also secured the message. using symmetric key encryption. And the great thing with this method is that we're using symmetric key for the encryption of the data and public key to prove the integrity and to perform the identity checking for it. So we can see that public key and private key, public key and symmetric key can work together and integrate both security and integrity. Okay, so that's been an overview of public key encryption. We tried to understand what it was, what some of the applications are, the main methods that we implement, and then we took a basic use case of how we could use symmetric key and public key encryption. You might also see this defined as asymmetric key or two keys, where in symmetric we only have one key. Okay, thank you.